In this section of chapter 13, I would like to discuss about solution process, which includes energy changes, solubility, saturation, supersaturation, and factors that affect solubility. Basically, we talk about intermolecular interactions, and there is a common saying that like dissolves like. That means the molecule, a solid molecule and solvent molecule must have certain properties in common. Like if one is polar, the other one needs to be polar, or it would be hydrogen bonding compound in order to be soluble. Then effect of temperature and pressure. Here we are going to define solutions, solvent, and solute. Solutions are a homogeneous mixture of two or more pure substances. Homogeneous means they make a single phase. For example, when you add salt to water and you mix it well, you would not be able to understand that salt is there because it would make a single phase. It would be the liquid phase. In any solution, the solute is dispersed uniformly throughout the solvent. Now there could be different types of solutions, and you see those examples underneath. There could be gas, liquid, liquid solid, solid gas, solid liquid, or solid solutions. In this slide, we are showing you solution process. Toward the bottom, you see these figures. The leftmost figure, the solute has been added to the solvent, and the solvent is water here. As time goes on, the solid molecules break down, and then solvent molecules surround those broken solute particles. And then finally, on the far right, you see that all these solute particle has gone into water solution. So basically what you need to learn is the intermolecular forces between solute and solvent particles must be strong enough to compete with those between solute particles and those between solvent particles. As solution forms, the solvent pulls solute particles apart and surrounds or solvates them. That we are seeing in those three figures at the bottom. Now, what kind of energy changes are involved here in solution process? Separation of solute particles needs energy. Also, separation of solvent particles needs energy. Now there will be new interaction between solute and solvent that releases energy. So these are the three major energy factors involved in solution process. Now, types of solution. There are three types of solutions: saturated, unsaturated, and supersaturated solutions. If you have a solute in contact with a solvent, say for example I have salt in the solvent, after some time the salt would gradually disappear into the solvent, and that's how it goes in solution. If you keep on adding salt, there is a limit that is reached. Initially it would go in solution, but after some time the number of salt particles going in solution would be the number of salt coming back to the solid, and that's equilibrium. And when it reaches equilibrium, you get a saturated solution at that particular temperature. That's the maximum amount of solute the solvent can hold. Let me explain to you this equilibrium which leads to saturated solution. On the left hand side, you're looking at solute particle just in contact with solvent. It didn't have chance to go in solvent making solution. As time goes on, what you're going to see is more and more of these solid would go from solid phase to the liquid solvents, and that's how it goes in solution. Question is it going to happen continuously for indefinite period of time? Answer is no. Here you are saying that after some of the solid goes in solution, so these are the solids that's in solution phase. If one of these solid goes to solution phase, one of the solid from the solution goes back to the solid. And this happens when it reaches equilibrium. So this is how we define equilibrium in dilution process, in solution process. The average number of molecules in each phase does not change with time when you reach equilibrium. Forward rate equals to reverse rate, just like any other equilibrium. Unsaturated solution. You have solute less than the maximum amount that at that temperature that solvent can hold, and that's unsaturated. That means if I add additional amount of solute, it would go in solution until it reaches saturation point. Supersaturation. In this case, the solvent holds more solute than normally possible at any temperature. These solutions are pretty unstable, and crystallization can happen by simple seed crystal or scratching the side of the flask, and that's what you're seeing on the right hand side figures. Factors affecting solubility. There is a common saying, like dissolves like. So polar substances tend to dissolve in polar solvents, and nonpolar substances tend to dissolve in nonpolar solvents. Now we are seeing some of these examples, like methyl alcohol or methanol is highly soluble in water. First thing is smaller in size. Secondly, it gives hydrogen bond pretty much like water. So let me show you that. So CH3 OH. Now water also has hydrogen bonding atom, and also it has oxygen. So you can have hydrogen, hydrogen, and keep in mind oxygen acts as minus, hydrogen as plus, plus. So this kind of bonding would keep methanol in solution. So that's why methanol is highly soluble. From methanol, if you get to ethanol, it still is highly soluble. Propanol is highly soluble. Then butanol, as you increase the number of carbon atoms, solubility gradually drops. So for example, when there are 4 carbons, let me draw those carbons. 1, 2, 3, 4 carbons, and OH group. Its solubility is quite small in water. What is going on here? Let me write down here this. These are all hydrogens. In this kind of compounds, carbon must have 4 bonds. So make sure you keep that in mind. Okay, now the carbon must have 2 hydrogens in order to satisfy 4 bonds, and oxygen can have only 2 bonds, and hydrogen can have only 1 bond. Now when you have 4 carbon alcohol, which is called butanol, it's not highly soluble in water. Why? This part of the molecule is not attracted towards water. This is hydrophobic. That means water does not like it, because remember I said like dissolves like, that part doesn't have any polarity or doesn't give hydrogen bonding. So it doesn't show much interaction with water. On the other hand, this end part shows interaction with water, but still this interaction with water for one little part out of the big molecule cannot still make a big difference in solubility, because major part of the compound is insoluble. So as you can see that as you go to the larger and larger compounds having more and more carbon, they are getting their solubility is very small. On the other hand, solubility in nonpolar solvent is quite high. So C6H14, that's 6 carbon compound. This is hexane, and hexane looks like this: 1, 2, 3, 4, 5, 6. Then you can fill in with hydrogen, and this is completely nonpolar compound. So just to save our time, I'm not filling all these with hydrogen, but keep in mind that each of those carbons must have number of carbon hydrogen bonds that gives altogether 4 bonds around each carbon. It is well known that cyclohexane is not soluble in water. On the other hand, glucose is highly soluble in water. Now why? This is glucose. If you look at the right hand side compound, that's glucose having quite a few of these OH groups. And these OH groups can interact with water, because these OH groups can give hydrogen bonding just like water. And that's why it's highly soluble in water. On the other hand, cyclohexane is nonpolar. It cannot offer hydrogen bonding. Just to remind you, in what situation hydrogen bonding is possible. When hydrogen is bonded to an electronegative element like oxygen, if you have this kind of bond, or fluorine, your hydrogen would be acting as a bridge, holding 2, 3, 4 molecules together. And that's called hydrogen bonding. Let me show you hydrogen bonding in water so that you'd be able to understand this. This is plus, oxygen, hydrogen, because oxygen is minus and hydrogens are plus. So always minus is facing a plus. So that's how it goes. And this is not the only molecule that's possible. There could be another water molecule in here, but we don't have enough space here. HOH. So that's how water is going to surround hydrogen bonding molecules all around. So in our example, water is going to surround glucose molecule, and that's why glucose is highly soluble. But it cannot do the same for cyclohexane, as it doesn't show any kind of polarity, so there is no positive or negative to attract water. Vitamin A is soluble in nonpolar compounds like fats. And again, this is also well known. Vitamin C is soluble in water. Now, can we understand that? The vitamin C structure is shown on the right. If you look at closely, there are quite a few OH groups, and each OH group, since hydrogen is bonded to electronegative oxygen, each OH can be contributing its hydrogen in hydrogen bonding with water. I'm just going to show you one of them. So this hydrogen can get bonded to water like this. Same would be the case the other ones, and this oxygen with pair of electron can get bonded to hydrogen. Always negative would be bonded with positive. Oxygen would carry negative charge delta minus and hydrogen would have delta plus. On the other hand, vitamin A has a big group which is nonpolar and non-hydrogen bonding, only a small group which have hydrogen bonding hydrogen, and it doesn't make a big difference because major part of the molecule is nonpolar and non-hydrogen bonding. Now, gases in solution. In general, solubility of gases in water increases with increasing molecular mass. That means heavier gases are usually more soluble than lighter gases, assuming that other factors are remaining the same. So you can see it as you go from the top towards the bottom. Krypton is much heavier and its solubility is much higher than nitrogen, for example. And also we know here that larger molecules have stronger dispersion forces, and that contributes to solubility. Solubility of liquids and solids does not change much with pressure. On the other hand, solubility of a gas in liquid is directly proportional to pressure. If you pressurize a gas, more and more of gas is going to dissolve in a particular solvent. In general, the solubility of a solutes in liquid solvents increases with increasing temperature. On the left hand side, you're seeing a graph, except for cesium sulfate. Other ones, you can see as the temperatures increase, solubility is increased. So in most cases, that's what happens. With increased temperature, solubility is increased when solute is a solid and you're dissolving it in a liquid. The opposite is true for gases. Carbonated drinks, which has carbon dioxide under high pressure, is more bubbly when stored in the refrigerator because it's cold. Also, warm lakes have less oxygen dissolved than cool lakes. And you're also seeing a graph on the right hand side that how solubility of gas decreases as temperature is increased. In this slide, we're going to discuss about hydrophilic and hydrophobic interactions and colloidal solutions. This is also a kind of solution where solute molecules are bigger than most of the solutes that we have talked about, but they're not that big to get settled out by gravity. So they would still be in solution and they'd be remaining as suspensions. Now there could be many examples of colloidal solutions that you're seeing on the far right. Milk is a colloidal solution. In case of liquid-liquid type of colloidal solution, we use the word emulsion. And in case of liquid gas, we say foam. Gas solid, we say aerosol. So all these different names are being used for different colloid types. Now, we're showing you one example of colloid in biological system. As I said that these are big molecules, relatively bigger solutes. They have hydrophilic end or water-loving end and hydrophobic end, that water-hating end. Phobia means fear or hating. The molecule folds in such a way so that the hydrophobic groups are away from water and hydrophilic groups are toward water. Now, let me give you an example of colloidal solution in biological system. In a small intestine, bile is secreted from gallbladder that contains a compound which is very similar to sodium stearate, and stearate is well known for emulsification of colloidal solution. Like normally fat would not go in water solution, but in presence of bile, fat in tiny small particles would remain as colloidal solution in water, and that's how our digestion, it helps in our digestion process. So in this figure you're seeing it, that how bile helps. It has one end, which is this end, which is hydrophobic, that attaches to the oil droplet or fat, and the charged end that faces water. So that's how the whole particle of fat goes in water solution as colloidal solution.